All right, thanks, Florian. And I want to emphasize what Florian said. Please stop me. That's the point of these, Chalk Talk style lectures. Excellent, cool. So today I'm going to tell you a little bit about quantum operations and the Kraus representation. Then we'll jump to the nil-la-flamme conditions for quantum error correction, which are based on the Kraus representation of quantum operations. And then we'll briefly introduce bosonic modes if there's time. Takahiro will talk about different quantum error correcting codes, and they're all going to be more or less based on bosonic modes. So I hope to have time to cover that. Cool. So to start, we're going to talk about density matrices. So density, oh, it's a great marker. Density matrices. And these are useful, or they're really necessary when your quantum system becomes entangled with its environment. And the point is that we don't have access to the environment. And so we have to, in some sense, trace over the environment. And you end up naturally, when you started off in a pure state, you might end up in a mixed state because you've had to trace over the environment. So generally, the density matrix is typically denoted by the Greek letter rho. And it's written as the sum on some sum over states, pj psi j psi j. And one more thing, my handwriting, as you can tell, is not fantastic. So please tell me if something is unclear with respect to that. Great. And where we guarantee that the state is normalized. And so we say that the sum on j pj is equal to 1. So this is a statement about the normalization of your quantum state. And this is a statement about the state of your system. The point is that this can represent a pure state, which would just be, there would be no sum. There would just be a single state. Or it can also represent mixed states when you have multiple states in this sum. So one important thing to note is that these states, psi j, are normalized, but not necessarily orthogonal. So a nice exercise, is to prove, so we want to prove that the trace of rho is equal to the sum on j pj, even if the psi j are not orthogonal. And then another nice exercise is to show that the density matrix, to show that to prove that rho is so-called positive semi-definite, which just means that if I take the overlap, if I look at the expectation value of rho with respect to some state psi, this is always going to be greater than or equal to 0 for all possible states psi. So the positive means greater than 0. Semi means it can be equal to 0. So these are nice things to try and prove. And the way that you would go about proving these is to expand each of these states in an orthonormal basis. And then you can show both of these things. Cool. Any questions on that? Cool. Great. So some important things to note about density matrices. We can compute all expectation values using the density matrix. So we would compute them via the expectation value of some operator O is equal to the trace of O with the density matrix rho. Another important thing to note is that rho has real non-negative eigenvalues. And this is, of course, implicit in the fact that rho is positive semi-definite. Or really, it's really a function of the fact that rho is Hermitian. So rho is Hermitian. So given that it's Hermitian, it has to have real eigenvalues, and they're non-negative because rho is semi-definite, positive semi-definite. Cool. And then the last thing is that if your state is properly normalized, then rho has unit trace summation on j, pj equals 1. So if your state is properly normalized, then it must obey this condition. Any questions on that? Cool. Great. So we have to use, so I want to emphasize again, we have to use the density matrix and mathematical functionalities associated with the density matrix to describe quantum error correction, because we're necessarily going to couple to the environment, we're going to lose information to the environment, and we want to be able to correct that. Great. Cool. Okay, so a natural question to ask is how does rho evolve? And we can answer, and we'll ask this question both unitarily and also non-unitarily. So question mark and question mark, right? So the question is, how does rho evolve if I only have sort of normal Hamiltonian dynamics? I don't have any coupling to any sort of weird environment that I'm losing information to. But then also in the context of coupling to a noisy environment, how does my density matrix evolve? And for that, so some important things to note is that this evolution must be completely positive, and trace preserving. And this is commonly denoted with the acronym CPTP, which is kind of fun to say. So completely positive, of course. So completely positive means that you have to guarantee this condition. So if you time evolve your density matrix, it always has to obey this condition. And trace preserving means that the sum on PJs should always equal 1. I should always have a properly normalized density matrix no matter what. Great. Right. Please.
And this is going back to the very first statement.
Yep.
Not all of us are chemists or physicists.
Yes.
Can you go back and do a brief introduction to density matrices?
Yes, great. So let's talk about an example. Let's talk about an example density matrix. So is everybody here familiar with like Braun-Ket notation? Excellent, cool. So let's consider some state psi, which is just which is going to be some superposition of my 2 qubit states. So I'll have alpha 0 plus beta 1, right? So how would I represent this as a density matrix? I would take bra psi, and then I would multiply it. I would take ket psi, and I would multiply it by the bra psi, and this would then be, so what does this actually look like in density matrix form? It's alpha 0 plus beta 1. And then how do I get bra psi from ket psi? I take the dagger of this equation. And so what does the dagger do? It turns the alpha into an alpha star, beta into beta star for complex conjugation. And then I get to flip these kets into bras. So then I have alpha star 0 plus beta star 1, right? So then this equals mod alpha squared 0, 0, multiplying these two terms, plus mod beta squared 1, 1, multiplying these two terms, and then I get the, these cross terms here. So alpha beta star 0, 1 plus alpha star beta 1, 0. So let's look at this density matrix. You can see immediately that the trace of psi equals 1, right? Because if I take the trace of so let's call this rho here. If I take the trace of rho, this is equal to what? This is the sum. This is the sum on. We'll do this on j rho j, right? This is how the trace is defined. And in this case, I just take j equals 0 or 1, 0 and 1, because those are the only states in my Hilbert space. And so these terms go away when I compute the trace, and I'm left only with these terms. So this is equal to alpha squared plus beta squared. And we know from normal not using density matrices quantum mechanics that alpha squared plus beta squared has to equal 1. Right? This is a statement of normalization. Great. So that's how I would write down a density matrix of a pure state, psi, so this is my pure state. We can also write down the density matrix of a mixed state, right? So an example of that would be so I'll call this rho 1 here, and then rho 2 I can write as maybe 1 on the square root of 2, 0, 0, plus 1 on square root 2. I'm sorry, this should be a 1/2, 1/2, and 1/2, 1, 1. This is similar to rho 1, right? It has these same coefficients here, or really what we can say, maybe we'll keep it general, and we'll have this be alpha squared, and beta squared. This is similar to rho 1, right? I have these same diagonal terms, but I've lost these off-diagonal terms, which I'll call coherences. They're normally called coherences because they tell you something about the superposition state that you were in initially. So in this case, in rho 2, I've lost any sense of there being a superposition state. I'm in a totally so-called mixed state of 0 and 1. Cool. Any questions about that? Cool. OK. Excellent. So the question we want to ask now. So Ray, did that answer your? Excellent. Cool. Great. So the question we want to ask now is, given some density matrix that could look like this, but we'll try and keep the discussion a little bit more general so that we don't just deal with qubits, although a lot of times we'll end up dealing with qubits. But so to keep the discussion more general, we want to ask the question, how does a state like this, psi, or actually how does a density matrix like rho, how does that evolve as a function of time? Yeah, Nathan.
So just one question. If you take a look at the plus state, you have 50-50 chance of measuring 0 and 1.
Yes.
But if you measure the maximally mixed state, you have 50-50 chance of measuring 0 and 1.
Yes.
Could you explain what the difference is between the maximally mixed state and the plus state?
Yeah, thanks, Nathan. So the difference between the maximally mixed state and the state plus, so what Nathan is pointing out is that if I measure rho 2, I have some probability alpha squared of getting 0, and I have some probability beta squared of getting 1. That's nominally the same as what's going on with rho 1, right? So what's the difference? What is the difference between rho 2 and rho 1? And the point is that I still have phase information in rho 1. I could do some sort of quantum gate. I could do some sort of operation to this state psi, maybe to put all of the population in the state 0. And then I could measure, and I would get, oh, I'm in the 0 state. And then, but for row 2, if I do that, I'm not going to get the same output because I'm in this totally mixed state and I don't have that same phase information. Yeah.
So what does the alpha star mean?
Sorry, yeah. So this means complex conjugate. So I'm writing alpha. I'm imagining that alpha is a complex number. So it's x plus I, y. And then alpha star means that whenever I see an I turn that into minus I. So it's x minus I, y. Cool. Excellent. Great. OK, cool. So let us continue. So the So the question is, how does rho evolve? And so with the Kraus, with the so-called Kraus representation, which is a lot more scary, which sounds a lot more scary than it actually is. So with the Kraus representation, the density matrix evolves as, which I'll call rho prime, which is rho of t plus some delta t, is equal to some sum on L, KL, rho of t, KL dagger. And I'm going to try my best to put little hats on things that are operators. And I will forget, and please stop me. Great. So what's going on here? And I'll say one more thing. And we also require that the sum on L of KL dagger KL has to equal not 1, but it has to equal the identity, right? Because these are operators. So the sum on this has to equal the identity operator, right? So it's maybe easiest to see what's going on here by considering a few examples. So let's consider the first example of just unitary evolution, right? What happens in this case? And we'll consider a time independent Hamiltonian H. So what happens in this case? We would say that rho of t plus delta t is equal to u rho u dagger, where u is equal to e to the minus I h delta t, and all of that over h bar, right? And that's basically it, right? So in the case of normal unitary evolution, this is the full expression for how my density matrix evolves as a function of time. And we know that u dagger u is equal to the identity, right? Because you can see immediately that if I multiply these two exponentials together, one of which has the I turned into a minus I, then I just get the identity operator. So this is one example of writing the time evolution of the density matrix in the Kraus representation. And the nice thing is that if you ever have a system that has only a single Kraus operator to describe its time evolution, then you know it must be totally unitary evolution. So the statement is that if you have more than one Kraus operator, then there must be some dissipation going on in your system. Any questions about that? Cool. Yeah,
Sorry,
please.
Can you explain why is it clear that if you have only one Kraus operator?
Right. So it is sort of a bit of an if and only if sort of thing. So if you only have a single Kraus operator that describes your dynamics, that is only satisfied in the case where all of your dynamics are unitary. So I'm not sure exactly how to rephrase that, but the statement is that if you can't decompose your time evolution into if you can't decompose it into less than 2 Kraus operators, then there must be some dissipation going on. One interesting thing that we'll talk about in a little bit is that the Kraus representation is not unique. So you can end up with lots of different sets of these KLs that describe the same dynamics. But if you only have one Kraus operator, then there's no, then that must be a unique, expression of what your time evolution is. So maybe I'll give one more example, and that maybe might make things more clear.
There are students who follow up, right? So
Yep.
in every case, you will have that, like your system is going to have a Hamiltonian, so you are going to have that time evolution.
Yes, you're going to have at least
So
one. That's right.
You're going to have something like that one with in that Hamiltonian representation. So
Yes.
you wouldn't be able to have a Kraus operator that cannot be represented, only one that can't be represented that way.
Right.
Because you have to be able to write your.
Yeah, you have to be able to write your time evolution in this way. That's right. Yes, exactly. Yeah. Great. Cool. So let's take an example where we actually have more than one Kraus operator, and we'll consider the example of amplitude damping. So amplitude damping. And in this case, we're going to suppose, that during time delta t, we have some probability, the probability of decaying from state E to G. And here I'm slightly switching notation from 0 and 1. So sometimes you'll see people write qubit states as 0 and 1, and sometimes you'll see people write them as E and G for excited and ground. Of decaying from E to G, the probability of decaying from E to G is P down gamma delta T. Right, so I have some rate of decay from E to G given by gamma, and then the probability that I decay over some time interval delta T is just gamma times delta T. Great. So what is the Kraus operator that will execute this decay? Well, it has to be K1, which is equal to the square root of P down times GE. Right? So what is this going to do when I apply it to some quantum state? It's going to take me from E, and it's going to put me in G. And then where does this square root come from? Well, you can see that this actually gives me the right probability that a quantum jump will occur. So if I compute the expectation value of K1 dagger K1, that's the trace of K1 dagger K1 times rho. Maybe people can't see over this thing. I'm going to continue over there. Right, so continuing from there, I had trace equals to trace of K1 dagger K1 rho. But we know that the trace is cyclic, so I can take this K1 dagger and I can put it over here. So trace of K1 rho, K1 dagger. And now I'm going to write I'm going to write my density matrix rho in sort of its most general form. So I'm going to write this as rho GG GG plus rho EE EE, where this is the entry of the density matrix corresponding to the GG and the EE operators. And then I have plus rho EG EG plus rho GE GE. Right? So what is this going to do? What is this going to look like? Well, if I take K1 and I apply it to rho, what's that going to do? It's going to select out the E component, so it's going to select out these two components. And then if I apply K1 dagger, so let's write down what K1 dagger is. What is K1 dagger is equal to still square root of P down times E G, right? So you can see immediately that I'm going to select out the EE component of this density matrix when I compute this quantity. So this is going to equal then, this is going to equal P, and I'm going to have, I get 1 square root of P down from K1 dagger, and I get 1 square root of P down from K1. So this is going to equal K down, P down, rho E E. So this gives me the right probability that I'm actually going to experience one of these amplitude damping events, right? It has to be proportional to the probability of experiencing a jump, which is P down. And I'm not going to experience a jump if I'm not in the excited state, right? So that's sort of the understanding of where this operator comes from. It has to be proportional both to the probability of having a jump and to the probability that I'm actually in the excited state. Any questions about that? Cool. Excellent. OK, so we've written down one Kraus operator, which corresponds to the jump that we've just described. And now we need to find what the other Kraus operator is. And the way that we'll do that is we'll rely on the normalization condition. So remember that we have this condition that the summation on L, KL dagger KL, has to be the identity, right? So let's write this as K0 dagger K0 plus K1 dagger K1, right? And now we know that this is equal to K0 dagger K0 plus, and then K1 dagger K1 is just P down times EE. Right? And then what is the identity? We remember that the identity is just the sum over both terms in our Hilbert space, right? And so now we can derive immediately what K0 dagger K0 is. So K0 dagger K0 is equal to, I'm going to move this over here. Well, let's just write it down. So K0 dagger K0 plus P down EE equals GG plus EE. So then we get that K0 dagger K0 is GG plus 1 minus P down EE. So that's just what K0 dagger K0 is. I want to find out what K0 is. And we can sort of, in some sense, take a square root of this equation. It's a little bit spooky because these are operators, right? But if I have an operator that's diagonal, meaning that its only entries are GG and EG without any cross terms, then you can imagine that I have some diagonal matrix. And if I want to take the square root of that, I just take the square root of each of the entries. So I have K0 is equal to GG, because the square root of 1 is 1, plus the square root of 1 minus P down EE. And you can verify for yourself that this actually, I recover that K0 dagger K0 equals that. Any questions about that? I'm sorry, it's P down. Anytime you see P with something that looks weird, it's down. So, yeah.
So with this G cross D and E cross C, are we referring that the function or the state will be either in the ground state or in the excited state?
Can you repeat that? Sorry.
So with the G cross D, are we referring that there is a maximum probability of having the states in the ground state?
So I'm just making a statement about what the Kraus operators are here. I'm not yet making a statement about what the state of the system is, right? So we're just trying to figure out how does the density matrix evolve? What Kraus operators will I use to describe that time evolution? So that's what this is going to do. But I'm not yet making a statement about the state of the system. Is there another question? Cool. Excellent. So one important thing to notice about K0 that bears repeating is that, so K1 describes, or K1 over there, it describes a quantum jump, right? And you'll notice I've forgotten hats everywhere, so apologies for that. So K1 describes having a quantum jump, and you could imagine that the other Kraus operator would just be the identity. It's not having a quantum jump, right? But that's not what happens, right? So K0 is explicitly not the identity. It's GG plus this weird square root thing on EE, right? So it's explicitly not just the identity operation. So what that tells you is that anytime you don't experience a jump, there's something really sort of fundamental here about what this is describing, which is that anytime you don't experience a jump, you're updating your priors about what the state of the system is, right? Every time you don't have a jump, you become more and more confident that you're actually in the ground state, because the only time you experience a jump is when you're in the excited state. So this decay over here is emblematic of this, of what's going on there. You could imagine that this describes decay of the probability of being in the excited state as a function of time. So there's something sort of fundamental going on there, and we'll talk a little bit more about that if that seems a little bit spooky. Cool. So let's use these Kraus operators now. So maybe this will be more clear once we write down actually how the density matrix evolves. So let's do that. So how does that density matrix evolve as a function of time under the action of these Kraus operators? So we'll find, so you would compute rho prime is equal to K0 rho K0 dagger plus K1 rho K1 dagger, right? So let's explicitly compute this. I think that might be a nice thing to do. So we have GG plus square root of 1 minus p down EE times rho. Maybe we'll just write out the first step. So GG plus square root of 1 minus p down EE plus, and then we'll have a p down out front, and then we have GE times rho times E G. So we can see that we have this. So I'm just using the definition of the Kraus representation, right? I'm writing down how my density matrix evolves as a function of the Kraus operators, as a function of time. And I'm sandwiching rho with K0, K0 dagger. And notice that K0 is the same as K0 dagger. There's because it's diagonal and there's nothing complex in the density matrix. And then I also have K1 dagger. And you notice that this selects off the excited state here, because that's the only thing that K1 does. It can take me from E to G, right? So it's worth carrying through this math. It's a few lines of algebra. And I'll just write down what the result is. It's going to be P down rho EE plus rho GG GG plus 1 minus p down rho EE EE plus the square root of 1 minus p down times rho EG EG plus rho GE GE. So we can understand where each of these terms is coming from, right? The probability that I remain that I'm in the ground state is given by the original probability that I was in the ground state, plus this additional term that comes from the fact that I can decay into the ground state with this probability, the probability p down times rho EE, as we discussed. This term here represents this update of your priors that I mentioned before. Every moment in time that you don't see a jump, you become more and more confident that you're not in the excited state, that you've always been in the ground state the whole time. So the probability that I'm in the ground state, rho EE, that goes down as 1 minus p down as a function of time. So this is a number that's going to be less than 1, but greater than 0. And then these terms are interesting. They represent a decay of the coherences that we mentioned before, right? So as a function of time, the amplitude of these entries in my density matrix are going to decay, and I'm going to go from the nice pure state that I had originally, and I'm going to decay down to the mixed state that we talked about before, right? So let's consider now, to gain a little bit more intuition for this, let's consider the case where p down is small, right? So this is a normal case that we consider, like here at Yale across the street, right? We have superconducting qubits, and they have pretty good lifetimes. The probability of having a decay from the excited state to the ground state is small compared with the gate times that we usually consider. So let's consider, so we'll consider p down much, much less than 1. And this could be any combination of the rate of decay being small or the time interval in which I'm asking the question being small, right, compared with 1. Right. Then we can expand this square root of 1 minus p down. So square root of 1 minus p down, I just Taylor expand this quantity, 1 minus square root of 1 minus x. And this is approximately 1 minus p down over 2. Right, and there are obviously corrections to that. So now let's ask the question, what does the coherence term look like in rho prime as compared to rho, right? It's equal to this quantity, 1 minus p down over 2 g rho E. So I'm comparing the entry in my density matrix that's the coherence entry. I'm comparing that at this later time, t plus delta t, to the original time. And we see that it's gone down by a factor of 1 minus p down over 2. We can also we can do the same thing for the diagonal entry of the excited state population. And this is 1 minus p down E rho E, right? And so this represents, again, this is just this entry of the density matrix. It represents the decay of the probability of being in the excited state. And so you'll notice this kind of interesting factor of 2 that appears here. And this is actually the same factor of 2. If you're familiar with coherence times of qubits, people always talk about T1 and T2, so very obscurely named quantities. But so in this expression for the so-called, this is the so-called coherence time. This is given by 1 over 2 T1 plus 1 over T phi. So this is the relaxation time. And this is the time that's the same. So it's the same thing as amplitude damping. So when I say relaxation or amplitude damping, those mean the same things. The rate at which I relax from the excited state to the ground state. And then this T phi is the intrinsic dephasing. Intrinsic dephasing time. So this factor of 2 here is the same as this factor of 2. So sort of what's going on here? I could have also included in this example some Kraus operator that looked like K2, which looked like some new rate, some square root of P2 times sigma z, or something, where this is the Z Pauli matrix, right? This would contribute to the intrinsic dephasing time. This wouldn't cause any jumps between the 0 and the 1, or the G and the E states, right? Because this is a diagonal operator. Forgot the hats again, right? But what it will do is it will cause these coherences to decay, right? So that's the contribution to the coherence time here. But jumps also cause the coherences to decay, because you can imagine if I have some superposition state and I have a jump, that's going to destroy the superposition state. So jumps must contribute to the coherence time, and they contribute in this way with this factor of 2. And you can understand where this factor of 2 is coming from in somewhat intuitively, where the point is that the point is that the decay of the probabilities is a decay of probabilities, whereas the decay of the coherences is a decay of amplitudes. And probability is amplitude squared. So that's more or less where this factor of 2 is coming from. So if that wasn't helpful, then you can forget about it. But that's some way to build intuition for where this 1/2 is coming from. Yeah.
We have a question limited in a minute.
Please.
But,
Yeah.
So if like that derivation on the left is only the first order.
This one.
No, one.
This one.
Right.
Yes,
Your
great.
It's only as true for small probabilities.
That's right.
But then the argument you just made about the factor of 2 would be exact.
So it's not exact.
Okay.
Right. Yeah.
So it
Yeah.
only
It's only sort of a first order thing.
it's useful for evaluating.
Exactly. So this is just a definition. So people often define their T2 in this way. And you can separate out these two contributions. You would do a so-called T1 experiment, where you prepare your qubit just in the excited state, and you watch for it to decay, and you get the T1 time from that. And then you separately do a so-called Ramsey experiment. So you would measure T2, so measure T1, prep E, wait for decay to G, and then to measure T2, you would do a so-called Ramsey experiment, after Norman Ramsey experiment, where you prepare a superposition state. You would prepare the state plus, which is G plus E. And this is sweeping a few details under the rug, but you more or less wait for that superposition to decay away. Then that's how you extract T2. And then you can separate out how much of your contribution to your T2, your coherence time, is coming from just T1 events, and how much of it is intrinsic dephasing. And so people in our field often say that we're trying to achieve T2 equals 2 T1, which means that you don't have any intrinsic dephasing. So that, yeah, but that.
But which would really mean T2 equals 2 T1.
Yes, is that not what I said?
You said T2 equals T1.
Oh, sorry. I think I muttered through it. T2 equals 2 T1. Yeah. Yep. Great. Great. Any more questions about that? Cool. Okay. So let's talk about quantum codes now. Right. So now we'll talk a little bit about. You may be asking yourself, these Kraus operators are nice, but are they useful? And what I want to try and convince you of is that they are useful, especially in the context of quantum error correction. So let's talk a little bit about quantum codes, and nil-la-flam. Great. So what is the task, QEC, what is the quantum error correction task that we try and accomplish? The goal, generally speaking, is to find find two logical code words. So, and by code words, I just mean states. And I'll call them W down and W up, so W for word. And we're going to embed them in a larger Hilbert space. So embedded in a large Hilbert space. And we want these to be robust, robust to errors KL that can occur. So the picture, before we do any math, the picture you should have in mind is the following. We have some block sphere, and this block sphere is going to describe what's going on with my code words, W down and W up, right? And let's say I have some state, and it's represented by this this polarization on the block sphere, right? So I'm in some weird superposition state. It's not fully W down, it's not fully W up, but it's some coherent superposition of the two. What I want to do is I want to engineer these states such that if an error occurs, say K0 or K1, that takes me to a totally different block sphere described by different states, which I'll call E down 1 and E up 1, but where the polarization of my block vector is unchanged, right? So you can imagine that an error occurs. It takes me from these two states, because if I have an error and I apply it to these two states, it's going to change the state. But I want to engineer it such that I have these two states, E down 1 and E up 1, such that the superposition that I had between the original states is maintained, right? And this should work for all possible errors that occur. So if I have some K2 that happens, I want the same thing to happen, right? This will be E down 2. This will be E up 2. And I want, again, for my block vector to be preserved. And this, you can imagine that this goes on. So this is the picture to have in mind for the task that we're going to try and complete, for lack of a better expression. Any questions about that? So it's a bit abstract right now, but we can make it more formal by writing down what are the so-called nil-la-flamme conditions for error correction. So the nil-la-flamme conditions are really just what's described in that mini figure over there. But the way that I would write down the nil-la-flamme conditions, so nil-la-flamme, is the following. I want for W sigma KL dagger KK, W sigma prime. I want that to equal alpha K, delta LK, delta sigma prime. So what's going on here? So let's talk about each of these terms in turn. So what's going on with the delta sigma prime? So well, let's first talk about this expression. What does this represent? The KK applied to W sigma prime, that represents the error state that I get when I apply the error KK onto this state. And similarly, KL dagger applied to W sigma bra is the same thing. So these are the so-called error words that I get when I apply these operators to my code words, right? So what is going on over here? So the delta sigma prime, why do I need this to be a delta sigma prime? This guarantees that it guarantees that the that error error words for the same error, but different basis states are orthogonal. So what does that look like in terms of this picture? It means that if I applied the error k1 onto w up and the same error k1 onto w down, I need them to land in different states. Because if they land on the same state, then there's no way for me to distinguish which state I started in, and hence no way for me to correct the error, right? So you'll be introduced to a code by my colleague Takahiro in the next lecture that does not obey the nil-la-flamme conditions, and hence errors are only detectable, but they're not correctable because we don't know where we started, essentially. Right? So that's where this delta sigma sigma prime comes from. And then what is this? What about the alpha k delta lk? This guarantees so delta lk means that I land on distinct Bloch spheres here, right? So then I know which error happened, and hence I can correct it. So guarantees that I know which error occurred. So that's important because I want to be able to correct the error. And importantly, so important. This should be, this alpha k part, alpha k must be independent of sigma prime, right? The problem if alpha k depends on sigma and sigma prime is that the environment will gain some information about what state I'm in if there's some dependence of alpha k on sigma and sigma prime. So maybe that will be more clear with an example. So let's consider an example. So actually, well, let's talk about it like this. So the first thing to note is that the probability of experiencing an error has to be the same for the code words. Said another way, alpha k is independent of sigma and sigma prime. So let's look at that explicitly. So p k down, which I'm defining as w down, k dagger, k on w down. This is nothing other than alpha k, right? Using this definition. And similarly, for p k up, I define it the same way. This is also equal to alpha k, right? So these are the same. So to repeat myself a third time, this alpha k does not depend. There's no dependence on the initial state here. And the point is that if there were dependence on the initial state, then I would have then my superposition that I so carefully engineered at the beginning would be at worst destroyed or at best perturbed, right? So let's consider the example where the error can only occur for one state. So error can only occur for one state, right? Let's imagine I had the starting state psi, which is lambda down, w down, plus lambda up, w up. And let's imagine that the error can only occur for one state, w up, right? What happens to this superposition state if I apply the error to it? Then I get the state psi prime, which is equal to, there's some normalization which we can carry around if we like. but then I get the state k on W up, right? So the final state has lost any information about this initial superposition state that I had. I've lost any information about the lambdas in this case. So this would not be an appropriate choice of code words if I had the error, if I had this error in my universe of errors that can happen. Right. Cool. OK, so one last thing I want to say about the null-Flam condition is that I wrote down a slightly simpler version of the null-Flam conditions than they're usually written as in their sort of full generality. So in full generality, so more generally, the null-Flam conditions are as follows. W sigma, F L dagger, F K, W sigma prime is equal to beta LK delta sigma sigma prime. So here we've lost the Kronecker delta over LK, and instead I just have some matrix beta, which is Hermitian. So this is generally Hermitian. So this is the way that the null-Flam conditions are generally written down sort of in their full glory. But one thing that maybe, where is that in my notes? So one thing that I forgot to mention is that the Kraus representation, and I sort of mentioned it in passing earlier, is that the Kraus representation is not unique. So note, Kraus representation is not unique. And the point is that I can define some new set of Kraus operators that are a unitary transformation of the original Kraus operators. So I have my fj's, which are some sum on k, u, j, k, 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 where u is unitary. And the point is that if my density matrix transforms as summation on k, 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 rho, k, k, dagger, I can just as well write that as summation on L, FL, rho, FL, dagger. And this is a nice exercise. Prove this equality here. So what this means is that I can take this more general form of the null-Flam conditions, and I'm guaranteed that I can put it in that form. You can think about that in multiple ways. One, I can transform my Kraus operators, but I also told you that this beta matrix is Hermitian. So if I diagonalize this matrix, that I can sort of back out what my Kraus operators are that obey the null-Flam conditions in this form. Any questions about that? Yeah.
Are there errors that causes logical states to be indistinguishable?
Right. So it depends on your code. And so my colleague Takahiro, who is in the back, he will tell you, I think, about a code that's called the dual rail code. And in that case, we have two states that can both experience the same error, and they collapse to the same state. And so this is something that does not obey the null-Flam conditions, because I end up in the same logical state. I end up in the same error state after the error happens. So you could imagine I start off with this nice Bloch sphere here, but then that error happens and I collapse down to a point because my error words are the same. So that's a case where the null-Flam conditions are not satisfied because I can't correct that error because I don't know where I started. There are cases where you can try and detect the error. And that's the nice thing about the dual rail code, but it's not generally correctable. Did that answer your question? Yeah. Any other questions?
I was just wondering, is there any other modularized space parameters involved in the possible cross operators?
So there's infinitely many Kraus representations.
But is there a space parameterizing all of that? Or?
I think the space parameterizing it is the space of all unitary transformations among the original Kraus operators. So yeah, whatever unitary transformation you like, you can write down is a totally reasonable representation to use. Cool. Right. OK, so I think that's probably a good place to stop at 10:30. I had some stuff on bosonic modes, but I think my colleague Takahiro will take it from here.